Hello everyone, here in this video we'll be discussing 2.6, which are limits at infinity, otherwise known as horizontal asymptotes, as we'll see soon. And I first want to start off by giving the intuitive definition of a limit at infinity. And we say that if f of x is defined on an interval containing infinity, or where one of the endpoints is infinity, I should say, because infinity is not real, so you can't actually contain infinity, but one of the endpoints can certainly be infinity. Then the limit as x goes to infinity of f of x is equal to L means that f of x approaches L as x gets larger and larger, meaning x approaches infinity. And similarly, we can have a different definition for x approaching negative infinity, but it's a very similar idea, and I'm not even going to bother writing it down. So you kind of change this to negative infinity to a, this to negative infinity, and you'll kind of see that x will get smaller and smaller in that case. So you can modify this definition to get a similar one for negative infinity limits, but that's all I want to see here. Now in this example, we want to find the limit as x goes to infinity of x squared minus 1 over x squared plus 1. Now if you graph this on the graphing calculator, you see that this will actually have a horizontal asymptote of 1. So that means as x gets closer and closer to infinity, the expression x squared minus 1 over x squared plus 1 will get closer and closer to 1. And there's actually a really nice way to see this, and it's something we actually have seen from algebra, where you have rational expressions, so quotients of polynomials. Basically, if the degrees are the same, you just look at the leading coefficients of these polynomials, which notice in this case is 1 and 1, and the quotient of those will be your horizontal asymptote. So really what we're doing is as x goes to infinity, all lower powers of x are negligible, and in particular negative 1 and positive 1 are negligible. Kind of think of adding 1 and negative 1 to infinity squared. Doesn't really make too much of a difference, because infinity, and even worse, infinity squared is going to be so large, subtracting 1 or adding 1 won't mean too much. So imagine being a millionaire and someone gives you $1. It won't really mean much to you because it's so small compared to what you already have. Probably not the best analogy, but just something to keep in mind. Now here we give this definition: y equals L is a horizontal asymptote of f if either the limit as x goes to infinity of f of x is L, or the limit as x goes to negative infinity of f of x is L. So basically, as x approaches infinity, we approach L, or as x approaches negative infinity, we approach L. So for example, with this one here, the image we actually get is something like this. And notice what that is actually a graph that has a horizontal asymptote at y equals 1. So as x goes to positive infinity, it approaches 1. And it so happens that as it approaches negative infinity, as x approaches negative infinity, it also approaches 1. So as x approaches infinity, it approaches 1. As x approaches negative infinity, it also approaches 1. But in reality, you need one or the other. You don't necessarily need both. Now, rational functions will actually always have both, basically, as it turns out. But some functions have two different horizontal asymptotes. This is a good example of one, tangent inverse, and we've seen this before, because recall the tangent inverse, we saw this in the previous video 2.5, actually has a graph that looks something like this. There is a horizontal asymptote at pi over 2, and another one at negative pi over 2. So as x goes to infinity, the y values will get closer and closer to pi over 2. As x goes to negative infinity, the y values will get closer and closer to negative pi over 2. So this limit here is pi over 2 because of horizontal asymptotes, and this limit here is negative pi over 2, again because of horizontal asymptotes. And also a nice way of seeing this is because tangent of pi over 2 approaches infinity from the right, and from the left, it approaches negative infinity. So that's kind of something you can try to visualize, but it's basically based on the graph of tangent. And notice this is really the graph of tangent, just kind of seen as sideways, which we know as a graph of tangent inverse. So now what we're going to do is we're going to move on and actually discuss something that will give us a better idea of how to discuss limits at infinity. Specifically, we're going to be seeing a lot of tools that will further this idea that I refer to here as as well, I said negligible, but there's a better word, and that's domination. So larger powers of x dominate over lower powers of x. And we'll kind of see why along with the technique to solve these limits at infinity. Right, so here we have this theorem. If r is bigger than 0 is a rational number, so a positive rational number, then limit as x goes to infinity of 1 over x to the r is equal to 0, and limit as x goes to negative infinity of 1 over x to the r is also 0. Now, a rational number means, if you don't know, is just a fraction of integers. So like 3 over 2, 2 over 3, 1 over 2, 5 is the same as 5 over 1, for instance. Not the square root of 2, that's an irrational number as it turns out. Pi, for example, is another irrational number. You can't actually write those as fractions of whole numbers. Okay, so why these are true, let's kind of take a look at this for a second. Basically, as x goes to infinity, any power of x will also go to infinity as well. So 1 over something that goes to infinity will actually approach 0. So that's kind of the idea behind this. As the denominator gets larger and larger and larger, but the numerator stays the same, the whole thing approaches 0. And what this kind of leads to is the idea I was describing earlier, which is domination. So here, what I'm going to do is I'm going to actually multiply top and bottom by 1 over x to the largest power in sight, which is x squared. So when you distribute 1 over x squared and then cancel, some kind of funny things happen. So what we end up getting is the limit as x goes to infinity of what? Well, it's going to be 3x squared over x squared, which is just 3, minus x over x squared, which reduces to 1 over x, minus 2 over x squared, over 5x squared over x squared is just 5, plus 4x over x squared is 4 over x, and then plus 1 over x squared. Now notice, as x goes to infinity, well, we'll just kind of pass a limit through each of these using limit laws, and each of these will go to 0. Each of these will also go to 0. Why? Because of this theorem here. They're 1 over x to a power. These are a number over x to a power, but it still actually works because of the limit law that involves a constant multiple of something that goes to a number. So this will go to that number times 0. So 4 times 0 and 2 times 0. But in any event, they go to 0. So what this whole thing actually approaches is just 3 over 5. Now notice we could have actually done that kind of a little quicker just by looking at the largest powers and look at the numbers in front of those and just kind of saying that larger powers of x dominate over lower powers of x as x goes to infinity. So if you ignore all lower powers of x and then cancel the x squares, you end up getting 3 over 5 anyways. So that really is kind of the more mature way of handling these. Sometimes it is best to just do this anyways for good practice and good measure. Here I'm going to try to do this with domination first to get an idea. So if you ignore all lower powers, this approaches 4x to the 6 inside the radical over negative x cubed. Now the square root of 4x to the 6 is actually, well, let's see, it's 2x to the third, and the x to the thirds cancel and you get 2 over negative 1, which is negative 2. But in this case, since we're approaching negative infinity, something a little different happens. Because as it turns out, if you plug in negative infinity into x cubed, that actually is negative infinity itself. So we'll have a double negative here. And that sounds a little bizarre, but let me just kind of tell you, and generally people are okay with this, otherwise I'd write a theorem to justify this. But we can actually change this limit going from negative infinity to going to positive infinity if we make the simple change of replacing all x's with negative x's. So let me rewrite this as the square root of 1 plus 4, and we'll write negative x squared, or negative x to the 6th there, 2 minus negative x to the 3rd. And let me write those negative x's in red, just to show that we've replaced all x's with negative x. And this intuitively makes sense because if x is approaching negative infinity, that means negative x will approach negative infinity when x approaches infinity. So perfect. And this will kind of get rid of that double negative problem we had here and allow us to kind of see it better. Now notice, if you recall, negative x to an even power is just x to that power, whereas negative x to an odd power, the negative will pull out because you'll have an odd amount of negatives. In other words, here the numerator is the same as 1 plus 4x to the 6th. the denominator here, this is going to be minus negative x cubed. So negative x times negative x times negative x is negative x times x times x. So that's going to be positive because of the double negative, x cubed, just like that. And again, we're still in the limit as x goes to infinity. Now this is good because if we have the understanding of domination, then we understand that this limit is actually the same as the limit as x goes to infinity of the kind of different expression, radical 4x to the 6th over x to the 3rd. So again, we're just dumping all lower powers and only leaving the terms with the larger powers, even if we have a radical in place, and that's okay. So now using, some simplification of radical here, the square root of 4 is 2, square root of x to the 6th is x to the 3rd, and again, we're still in the limit as x goes to infinity of 2x to the 3rd over x to the 3rd. And now the x cubes cancel, so we end up here, what we end up with here is just 2, opposed to that negative 2 we saw earlier, but again, the double negative kind of made it be positive 2 anyways. So the answer here is 2. Now, if you wanted to do this by multiplying everything by the largest power, you would multiply everything by 1 over, well, I meant to say 1 over large power. You'd multiply top and bottom by 1 over x to the 3rd. Now, you may ask yourself, well, the largest power inside is x to the 6th, but it's the square root of x to the 6th, which is x to the 3rd. So actually, if you multiply top and bottom by x to the 3rd, but in the numerator, call it 1 over radical x to the 6th and bring that inside the radical, then you'll see some cancellations kind of like we saw here, and then we'll get terms that go to 0, and you'll basically be left with this anyways, and you'll get this as a consequence. But I just think this is probably the better way of handling it. Notice if you were to do it that way, it would be at this point. In other words, you would still have to do this change from negative infinity to infinity in the limit. All right, so now we're going to take a look at an example that's pretty similar to this, but at first glance it doesn't appear to be. Right, so here we have these 3 examples. The first 2 are kind of similar, but the way I want to handle the first 2 actually is by trying to write them as fractions so we can use domination. So at first glance, you would want to, if you consider domination, ignore the 1, radical x squared is just x, and x minus x is 0. So intuitively, this would be 0. Similarly here, if you ignore all lower powers of x for this radical part, you get just radical x squared, and that's just x, and x minus x is 0. Now, as it turns out here, that domination idea actually kind of works. Here it doesn't, because if we're ignoring the lower powers of x squared here in the radical, why aren't we ignoring this x outside, even though it's kind of equivalent to this radical x squared? As it turns out, this x actually makes a little bit of a difference because it's a variable, opposed to this 1 doesn't really make too much of a difference because it's a constant essentially. And in fact, if you wanted, you can modify this question by replacing 1 with 3 or something like that and see if you get the same result we're going to get right now. But the first thing I want to kind of give us the understanding of is the problems we looked at before, fractions, rational expressions, those are kind of what you want for limits at infinity. So since these are limits at infinity, we'll try to write them as such. So I'm actually going to consider this as a fraction of itself over 1. And what this now should remind you of is a scenario where we have a radical expression, and what we want to do is multiply top and bottom by the conjugate. So I'm going to multiply top and bottom by the conjugate of this expression, which is radical x squared plus 1 plus x, and then for the denominator as well. Okay, good. Now notice in the numerator, we just get a difference of squares. So the first one squared is the radical squared, which cancels out the radical and just gives us x squared plus 1 minus x squared. And you'll see that the x squareds cancel, which is nice. And then we have this in the denominator. Great. And then, of course, limit as x goes to infinity. I think we're good. So notice, again, the x squareds cancel, so we just have the limit as x goes to infinity of 1 over this. And as x goes to infinity, here this is a sum. So this whole expression in the denominator is not an infinity minus infinity scenario, which, by the way, is, even though I didn't mention it, infinity minus infinity is actually an indeterminate form, much like how 0 over 0 is an indeterminate form. But that's a discussion for a much later time. But here, infinity plus infinity for the denominator will actually always approach positive infinity, which intuitively makes sense. But at the same time, because of domination, we can say that this 1 is negligible. So we have radical x squared plus x. Radical x squared is just x. It's actually absolute value of x, but since x is approaching infinity, it's assumed to be positive. And notice x plus x is just 2x. So really we can pull the 1 over 2 outside, and we know the limit as x goes to infinity of 1 over x is 0. So this is 1 over 2 times 0, which is just 0 itself. So indeed it's the guess we thought it was previously. And you can kind of see that this last part, well, here we had 1 over this expression, and this expression is 1. If we changed the 1 to 3, let's say, this would be 3 over, it would still be 2x actually, because this 1 we kind of ignored for the last step here. Now, that last step you can kind of handle a little bit differently. You can actually multiply top and bottom by 1 over x, by 1 over x. And just to show you, because I feel we deserve to see that, let me just write it here, even though I'll erase it shortly. So what we had was this, 1 over, and I'm going to not write the limit part, just so I don't write too much. So we multiply top and bottom by 1 over x, which is the largest power. We get 1 over x on the top. In the denominator, if you distribute this 1 over x over x is 1, so the last term will be positive 1. When you distribute it into the radical, though, you have to consider this 1 over x as 1 over radical x squared. So I'm distributing 1 over radical x squared into the radical x squared plus 1. In other words, we can write this all as all under one radical, x squared plus 1 all over x squared, which reduces as x squared over x squared, which is 1, plus 1 over x squared. Again, all under that radical. So that's what the first term really becomes once you distribute 1 over x. Okay. And now we can clearly tell that, let me kind of see here. Yeah, we can clearly tell that this goes to 0. So the whole thing will approach 1 over x over 2. But 1 over x also goes to 0. So the whole thing actually approaches 0 over 2. So this certainly makes sense because it's not 0 over 0. And I think this is kind of our savior, this 1 here, and I guess this 1 here as well. Because even if the radical part went to 0, this 1 would make the denominator not 0 anyways. And again, that's just another way of kind of viewing this, but I think domination is a better way of viewing it. But that's maybe just my opinion, I don't know. So now we're going to move on to the second example where you may think, well, it's the same thing. Because it's still infinity minus infinity, and anything minus itself is 0. But again, like I mentioned, infinity minus infinity is actually in indeterminate form, meaning it is not always the same value. It's to be determined, kind of, depending on the functions. So we're going to do the exact same thing. We're going to treat it as itself over 1, multiply top and bottom by the conjugate, and see what happens. Now when we do that again on the top, we get a difference of squares. The radical squared cancels the radical and just leaves you with x squared plus x. And then minus x squared. All over what? All over radical x squared plus x. And notice these x squares cancel. We're still in the limit as x goes to infinity. Perfect. And now if we divide top and bottom by 1 over x, much like we kind of did in the box that I just erased. Well, let's see. So I'm going to divide top and bottom of this by x. So x over x is just 1. X over x in the denominator here for the last term is also 1. And remember, if we divide a radical by x, we divide each term inside the radical by x squared, because x is the same as radical x squared. So x squared over x squared in the radical is 1. And x over x squared in the radical is 1 over x. And here in this case, because the numerator is x, so dividing by x doesn't doesn't actually go to 0 in the limit, it goes to 1. So we get a different answer here now. And this actually approaches 1 over, because 1 over x goes to 0 as x goes to infinity, 1 over radical 1 plus 1, which is 1 over 2. Now there's kind of a different way of viewing this, again, by domination, here at this point. So by domination, we can say all lower powers of x are negligible. In the top, we only have x. In the denominator, this x can be ignored as x goes to infinity. So we have radical x squared, which is x, and x plus x is 2x. X over 2x, the x's cancel, and you get 1 over 2 indeed. I also just kind of want to mention here that there is even another way of handling this limit by using completing the square. But that's honestly a little much, but there is a way to do it. It's kind of cool to see, but we just don't have time to do it here. This is probably the more traditional way. If you want to look into it, I'm sure there are ways of seeing that online. But lastly, finally, for this part of this video anyways, we want to take a look at this example. As the limit as x goes to 2 from the right of tangent inverse of 1 over x minus 2. Now notice, at first glance, this is not a limit at infinity. But it actually kind of is, because notice, as x goes to 2, the inside here will go to what? The inside here will go to 1 over 0, because 2 minus 2 is 0. Now notice that 1 over 0, we kind of saw that depends on what function we're looking at. 1 over 0 could be positive infinity or negative infinity or both, meaning the limit wouldn't exist. But here, since we're looking at a one-sided limit, the limit will always exist. And specifically, when you're plugging in numbers that are larger than 2 into 1 over x minus 2, you get 1 over a number bigger than 2 minus 2, which is positive. So 1 over a positive number, as x goes to 2, this will approach 1 over 0, which we know to be positive or negative infinity. But again, since we're approaching 2 from the right, this will be positive. It'll attain only positive values, so this will actually approach positive infinity. In other words, we can basically do the following substitution. We can replace this with infinity. So how do I describe that? I guess we can make a few substitutions to show you. I haven't even shown any substitutions in this class yet. But basically, we want to let's call it t. We want to let t be equal to x minus 2. And notice, since x is approaching 2 from the right, then what would t be approaching? Well, if you plug in 2 from the right, you get, well, 2 minus 2 is 0, so that would be t from the 0. That'd be 0 from the right, I meant to say. So using the substitution, this becomes the limit as t goes to 0 from the right, because it's attaining positive numbers, right? 2 minus, numbers bigger than 2 minus 2 are positive numbers, of tangent inverse of 1 over t. Great. Now the last substitution I want to make is to say the following. When t goes to 0 from the right, 1 over t will approach infinity. So really this is the same as the limit as, let's, I don't want to go back to x, I guess let's use, don't want to use a, I guess we could use u. The limit as u goes to infinity of tangent inverse of 1 over, not 1 over u, but just u itself. So really what I'm saying here is that as t goes to 0 from the right, then 1 over t approaches infinity. So essentially I'm using the substitution, u is equal to 1 over t. So we're replacing 1 over t with u, and we're saying that as t goes to infinity from the right, u will go to infinity. So if t approaches not infinity, but I meant to say 0 from the right, this implies that u will approach infinity, positive infinity. Because 1 over t approaches infinity if t approaches 0 from the right. And we've seen this limit before. This is just, well, pi over 2. Awesome. Now again, there are more intuitive ways of kind of seeing that, but I'm kind of done with these examples. I've taken a little bit too much time here. And now we're going to move on to one last idea, and it's going to be a little short, and that'll be the end for 2.6. Okay, so here I want to look at this fact, and once we've established the fact, we'll see an example that the fact is applicable to, and then finally we'll look at these kind of strange and kind of intuitive examples afterwards. So there's no really justification as far as what we've seen so far to establish the results here. I'm just going to establish them by kind of convincing you logically. So let's see. So first we want to take a look at the limit as x goes to negative infinity of e to the x. Now remember from what we saw when you have x approaching negative infinity, you can actually change this to the limit as x goes to positive infinity, but what must you do? You must replace x with what? That's right, with negative x. I don't know if you actually said it, but if you did, great job. And yeah, e to the negative x, notice is just 1 over x, so this is actually limit as x goes to infinity of 1 over e to the x. And this should remind you from what we saw as far as limit as x goes to infinity of 1 over a power of x. Power of x, as I said, goes to infinity as x goes to infinity. E to the x is similar. Remember that the graph of e to the x looks something like this. This is y equals e to the x. So as x approaches infinity, so does e to the x. So the denominator here is approaching infinity, where the numerator is just staying 1. And when the denominator blows up to infinity, but the top stays 1, this whole thing actually goes to 0. So that means this limit is actually 0. Great, so that's the fact I wanted to establish first, and I'll kind of box this. So that's kind of a fact, kind of like how limit as x goes to infinity of tangent inverse of x goes to pi over 2. That's also a fact. And similarly, as x goes to negative infinity, it goes to negative pi over 2. And now I'll actually handle this example where I said that this fact is going to be referenced. So, what must we do? Well, let's think about this for a second. We're approaching 0 from the left. And kind of like what we saw previously, we want to see what happens as 1 over x, well, what happens to 1 over x as x goes to 0 from the left. So in the previous problem we saw, it didn't look like an infinite problem, limit at infinity problem, because x was approaching 2 from the right. Here it's approaching 0 from the left. But notice 1 over x goes to what? Well, again, if you graph 1 over x, we can clearly see that 1 over x goes to negative infinity if you approach 0 from the left. As you approach 0 from the left, it's going down towards negative infinity. So what this tells you is that you can actually rewrite this as a limit as x goes to negative infinity of e to the x. Now I know this is a little strange, and based on the previous example, we probably should use a substitution. So let me use a t instead of x here. And let me just kind of say that we're letting t be 1 over x. So notice, as x goes to 0 from the left, t will approach negative infinity. So we'll replace the limit part with t approaching negative infinity, and then we'll replace 1 over x with what it's equal to in the substitution, which is just t. And this is legitimately just the fact we saw previously, so the answer here must be 0. Great. And now we'll look at these two examples, which I said are kind of afterthoughts, I guess you can say, but at least they're pretty nice, and we're going to go over them. So here, this is the limit as x goes to infinity of sine of x. Now, if you graph sine of x, we've graphed sine of x a bunch already. We have this kind of oscillating function that grows to positive 1 and then goes back down to negative 1 infinitely often. In fact, if you look at this, there's no horizontal asymptote, it just kind of keeps going and going and going and going. If the function did something like this, and it still kind of oscillated, but it got smaller and smaller and smaller towards an actual value like the x-axis, for instance, then it would actually have a horizontal asymptote and this limit would exist. But unfortunately, otherwise, as is, this limit does not exist because it doesn't actually approach anything as x goes to infinity. It'll just keep bouncing in between negative 1 and 1. Great. So this limit doesn't exist. This limit, however, kind of doesn't exist, but it kind of actually does. So we can call it something opposed to this. So let me try to describe it to you. What you can actually use here is the idea of domination. And we can actually say as x goes to infinity, the numerator, well, the only term in the numerator that really makes a difference is the largest power, which is x cubed. And in the denominator as well, the largest power is just x squared. And notice x cubed over x squared is just x. So really we have the limit as x goes to infinity of just x. And as x goes to infinity, x goes to infinity. So the reason why I said this kind of doesn't exist is because infinity isn't a real number. So the limit goes towards infinity or tends towards infinity, which is what we normally say. But one could also say the limit doesn't exist, meaning that the limit doesn't approach a real number. So that's another way of kind of seeing it, but we're just going to say it's infinity because we have that understanding there. All right, so that was the end for 2.6. I really hope you enjoyed the video. I'll see you in the next videos for 2.7 and 2.8. Thanks for watching. See you then.